In this video, we solve problem 13.3.052 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the partial derivative of f with respect to x and the partial derivative of f with respect to y, and evaluate each at the given point. So we have this function here, and the point is x equals 1, y equals 1. What I would recommend, since this is a quotient, is that we use the quotient rule in both cases. But when we take the derivative of the numerator, we're going to have to use the product rule. And when we take the derivative of the denominator, we'll have to use the chain rule. And actually, in the numerator, maybe we won't have to use the product rule because when you take the partial derivative with respect to x, you'll be treating y as a constant. And when you take the partial derivative with respect to y, you'll be treating x as a constant. So let's do the partial derivative of f with respect to x first. Now remember how this notation works. This says the partial with respect to x of whatever is in the brackets to the right of that expression. So we have 7xy divided by that square root. Now we all know that a square root is the same as a 1/2 power because that's raised to the first, and then there's an implied 2 for the index there. Since we are about to use the chain rule and the outside function is that 1/2 power function, it's helpful to rewrite that as that 2x squared plus 2y squared raised to the 1/2 power first. And then we'll just apply the quotient rule, and then whenever we take the derivative of the numerator and the derivative of the denominator, we'll use the appropriate rules for that as well. So according to the quotient rule, we get the bottom function times the derivative of the top function, where with the mnemonic it's low d high, derivative of the high function, with respect to x, treating y as a constant, minus high d low, with respect to x, treating y as a constant, all divided by low, that's the bottom function squared. And of course, if we take 2x squared plus 2y squared to the 1/2, and we square it, due to our exponent properties, we're going to multiply that 1/2 and that 2, and we're going to have just the 2x squared plus 2y squared. Okay, so now the only thing left to do is compute this derivative and compute this derivative, and then simplify as much as we can. So this term, or that expression, actually just gets pulled down, and then we're taking the derivative of this expression. So I'm thinking of this as a constant times x because I'm treating y as a constant. The derivative of a constant times x is just the constant. In this case, our constant is the 7y. And then I'm subtracting 7xy times the derivative of this expression. Well, this expression is a composite function. I've got a function nested inside that square root function. So my inside function is actually that 2x squared plus 2y squared, and the outer function, the outside function, is that 1/2 power function. So we know whenever we use the chain rule, we first take the derivative of the outside function. The derivative of a function to the 1/2 is that function, or 1/2 times that function to the negative 1/2. And you put the inside function back inside without doing anything to it yet. And then you multiply by the derivative of the inside with respect to x, treating y as a constant. The derivative of 2x squared with respect to x is just 2 times 2, which is 4, times x to the 1 less power, plus the derivative of 2y squared with respect to x, treating y as a constant, is just 0. Because it's just like having a 2 times 3 squared there. It's just a constant. So this is our answer. It's just not simplified. You can simplify the 2 or the 1/2 and the 4. That'll give you a 2 right there. So we'll have this 2x squared plus 2y squared to the 1/2 times 7y minus, and you've got 7xy times an extra x. that's 7x squared times y. And if you want, since you have this expression to the negative 1/2 power, you can put that in the denominator. If you make that 1/2 power a positive 1/2 power. And then you're dividing all of that by the quantity 2x squared plus 2y squared. Now, we don't typically leave our answer like this, where you have a fraction inside a fraction. Most of the time, in order to get rid of that complex fraction, we will multiply by the LCD of the smaller fractions. Since this is the only fraction with a denominator that's not equal to 1, the LCD is just equal to that denominator. So we're going to take the entire numerator of this larger fraction and multiply it by the denominator of this smaller fraction. And remember, when you do that, your multiplication distributes over addition or subtraction. So this gets multiplied here, and then we're dividing by that there. Now we can't just multiply the numerator by that without also multiplying the denominator by that. And now you've got a 2x squared plus 2y squared raised to the first times that same expression to the 1/2. Due to our exponent properties, we're just going to have the 2x squared plus 2y squared in the denominator, and we have a 1 plus a 1/2, which is 3/2. And then when we distribute here, this times this, I've got the square root times the square root. It's just going to leave what's inside that square root. In this case, that's 2x squared plus 2y squared multiplied by the 7y here. And when we distribute here, these denominators are going to reduce, and you'll just have the negative, or this denominator will reduce with that in the numerator, and you'll just have the negative 7x squared times y. So from here we can simplify. We'll have 14x squared y plus 14y cubed minus 7x squared y, all divided by this expression. And I've got 14 of those over here, and I'm subtracting 7 of them, so I actually have 7 of them. So we have 7x squared y plus 14y cubed, all divided by 2x squared plus 2y squared to the 3/2 power. I would probably leave my answer like that, but you could factor out a 7 and a y as well if you wanted to. Actually, I just realized that I'm missing a term. I forgot that too. It's actually not a term. I'm missing a factor. We have the 7 times x times y times 2x. This should have been a 14. The 7 times the 2 would have given me a 14x squared y there, which would make this a 14x squared y, which would make this a 14x squared y. And then this term, or this expression, would reduce with that expression, and we would just have the 14 y cubed in the numerator. Sorry about that. Glad I caught that mistake. Okay, so now if we want to evaluate this expression at x equals 1, y equals 1, we'll have 14 times 1 cubed over 2 times 1 cubed plus, or 2 times 1 squared times plus 2 times 1 squared raised to the 3/2. So we have 14 over 4 raised to the 3/2. So that's going to be 4 times 4 to the 1/2. Or if you prefer, you can call that 4 times the square root of 4, which is 2. This is 7 times 2 in the numerator, and the 2's reduced, so you end up with 7 over 4. So that's our partial derivative with respect to x evaluated at 1, 1. Now, we were actually done computing the derivative when we got to this point, if I had brought that 14, or multiplied the 2 and the 7 to get the 14 here, but it wasn't simplified. When we simplify it, do all that extra algebra, we get to this nice sort of clean fraction, which is a little bit easier on the eyes and probably more like what WebAssign is looking for. Okay, now let's do the same thing for the partial derivative of this function with respect to y. Now, I think I already know the answer because look at this function. If I replace the x with y and the y with x, if I just switch them, I would still have 7 times x times y because y times x is the same as x times y. And if I switch the x and y here, I would have the exact same expression. So I bet the partial derivative of f with respect to y looks just like this. But everywhere you see a y, you should replace it with an x. And everywhere you see an x, you should replace it with a y. But 2x squared plus 2y squared, or excuse me, 2y squared plus 2x squared is the same as 2x squared plus 2y squared. Because multiplication, or excuse me, because addition is commutative and you can add in any order that you want. So we have that there. I bet this is the answer. But let's actually prove that to ourselves. So that means we should have 7 over 4 here for the partial derivative of f with respect to y at 1, 1 as well. I'm saying by symmetry we should get the same thing, but let's prove it. Okay. So we're taking the partial derivative with respect to y of this quotient. Remember, operator notation, that's not multiplication. That's the partial derivative with respect to y of whatever's in the brackets. The derivative is this, according to the quotient rule. It's the bottom function times the derivative of the top function with respect to y, treating x as a constant, minus the top function times the derivative of the bottom function with respect to x, or excuse me, with respect to y, treating x as a constant. I may have said that backwards in that other one. We're taking the derivative with respect to y, treating x as a constant in both cases. That's low d high minus high d low over low low. And if I take a square root and I square it, I just get the expression under the radical. Okay. And remember with that mnemonic, d low, d high, the d as an operator as well, it applies to the high function. So it's the derivative of the top function minus high d low. That's the derivative of the bottom function. Okay. I'm thinking of the x as a constant. So this is the derivative of a constant times y with respect to y. The derivative of a constant times y is just the constant. So we just bring down our 7x. And then over here, got to use the chain rule again. Same idea as before. The outside function is that 1/2 power function. So we're going to bring our power down. Whoops. Multiply by that expression to the negative 1/2 power. Put your inside function back inside. Don't differentiate it yet, just put it back in. And then take the derivative of the inside with respect to y, treating x as a constant. Well, if x is a constant, 2x squared is a constant, so we get 0 there. Plus the derivative of 2y squared, which is 4y. And the 1/2 and the 4 simplify, that'll give us a 2y there. And again, we're going to have a fraction. That's what's implied by that second. That 1/2 power that's negative there. So we're going to have 7xy times 2y is going to be negative 14xy squared. We've got the square root, or if you prefer, 2x squared plus 2y squared to the 1/2 in the denominator, and then there's a much larger denominator. Sorry, I don't know what I did with that pair in there. It's kind of getting late and I'm tired, that's why. All right, so we're here. And then we multiply everything by this LCD, least common denominator of the denominators within our fraction. And we distribute. So this times this is going to give us, well, a square root times a square root is just going to be the expression under the radical. And remember that 1/2 power is the same as a square root. And here, when we multiply these together, this will reduce with this, and we'll just have the negative 14xy squared. We multiply those together, the base is the same, we add the exponents. So there we are. Distribute your 7x. So we'll have 14x squared times x is x cubed, plus 14xy squared minus 14xy squared. That's nice, always nice when that happens. And these guys reduce, and we get exactly what we expected to get due to the symmetry of the function itself. You could switch x and y in that function and you would have exactly the same function. So when you take the derivative with respect to y, you should get pretty much the same thing. You just switch the x's and y's as well. And if we evaluate this at 1, 1, our numerator is clearly 14. 14 times 1 cubed is 14. And then we'll have 2 plus 2 in the denominator raised to the 3/2. So that's 2 times 7 over 4 times the square root of 4. 2 and the square root of 4 reduce, and we end up with 7 over 4 again. Yep, and that's exactly what we expected from the symmetry of that function.